Hi, everybody. We are going to talk about section 3.5 today, which is all about symmetry. This is, I think, by far the easiest section in chapter 3, so it should be pretty simple for you to do just through a video here, especially because you probably already know what symmetry is. You've seen it in other classes, you've seen it outside of class in just regular life, so you're probably pretty well versed in this already. There are 3 kinds of symmetry that we're going to talk about: reflectional, rotational, and point symmetry. So reflectional symmetry happens when you can draw a line in a shape and reflect that shape back onto itself. So for example here, if you have this shape and you are able to draw, it's not a very good shape, but that's okay. If you're able to draw a line through it and that line has the same shape on both sides, that would be a line of reflection, having reflectional symmetry. So symmetry, where a reflection maps the figure onto itself. The next type of symmetry is rotational symmetry. So in this case, we're going to take a shape and we're going to rotate it, and we're going to end up with the same shape. So for example, the letter Z has rotational symmetry, because if I take this letter and I make a dot right in the center and I spin it around, and I can't really do that on this program, but if I spin it around, I'm going to end up with the same shape as I started with. I can spin it halfway around, and that will be a rotation. Let's see, maybe I can actually do this. And can I rotate it? Does not appear that I can rotate it. Okay, so unfortunately I can't show you, but we're turning it less than 360 degrees and it's going to look the same. So symmetry, where the image is mapped onto the pre-image, where the image is mapped onto the pre-image after a rotation less than 360 degrees. After a rotation less than 360 degrees. And the reason that it's important that we say less than 360 degrees is because every shape is going to rotate onto itself when we rotate it 360 degrees. So it's not special that if we rotate something all the way around, it ends up on itself. It's more special if we can rotate it part way around, and it will end up on itself. And then the last one is point symmetry, which is a special name for 180-degree rotational symmetry. 180-degree rotational symmetry. So if we can take a shape and we can rotate it 180 degrees or a half turn, and it looks the same as it did before, that means it has rotational symmetry. So if we have this shape and we rotate it around the center, we rotate it a half a turn, we'll get the same shape as we had before. So it has point symmetry, which is just a special kind of rotational symmetry. So the first thing we want to do here is identify the transformations for symmetry, whether that would be a rotation or a reflection, that would allow us to map the figure onto itself. So for example, this first one, we've got the smiley face. And since we would be able to draw a reflection line through the smiley face, then this is going to have reflection symmetry, because we can draw that line and have the same thing on both sides of the line. This next shape, again, we could draw a line in it. We could draw multiple lines in it, and we could get those reflections that had the same thing on both sides. So this has reflection symmetry. But this shape also has rotation symmetry. If I took the shape and I spun it around 180 degrees, it would map onto itself. So we could use a rotation to map this shape onto itself as well. And then this last shape, same thing. I could reflect over certain lines. Apparently, I'm really bad at drawing them. There we go. So we could do a reflection and get the same shape. But once again, we could also rotate it around this point in the center 180 degrees. Another way to think about that is that it would look the same upside down as it does right side up. So we could use a rotation as well. So coming down here, we've got some ideas. That's how many lines of symmetry does a regular hexagon have? So when we think about this word regular, regular has a different definition in geometry than it has in the rest of life, because regular in geometry means it's a shape with all sides the same length and all angles the same length. We'll see if this program allows me to draw a hexagon and understand that I mean, yes, perfect. So, all right, so here's a regular hexagon. When we're looking for lines of symmetry in a regular hexagon, we can say, well, there's one that's straight down like this, and there's another one that's going to be the same thing going this way, and another one going through here. Plus, we've got 3 more lines of symmetry that go through the points of the shape here. So there's 1, there's 2, and there's 3. So technically, there are 6 lines of symmetry in a regular hexagon. Then we come down here to this rectangle and we say, how many lines of symmetry does this one have? This rectangle only has 2 lines of symmetry. One that goes right here and one that goes through the side like this. A lot of people want to say that there's a 3rd line of symmetry from corner to corner because we are able to draw a line from corner to corner. It's not a very good line. Let's see. Like this. However, that doesn't mean it's a line of symmetry. If we took this rectangle and we folded it across that line, those edges would not match up. We don't have the same pieces reflected over each side of that line. So that's not one of the lines of symmetry. So this shape has 2 lines of symmetry. We know that we have found them all because after that, we can't find another line where when we reflect the shape over itself, it stays the same. Down here, we're going to look at rotational symmetry. For what angles of rotation does the figure map onto itself? And do the figures have point symmetry? So for rotational symmetry, we want to identify the angles that cause the shape to be symmetrical. So here, first of all, we have an equilateral triangle. And in this equilateral triangle, we can say, all right, how many degrees would we need to rotate this triangle around its center in order to make it look exactly the same? So if we took this point and we rotated it down to here, the whole shape would rotate around, and that would work. So that would be like 1/3 of a turn. 1/3 of the way around 360 is 120 degrees. But after we rotated it 120 degrees, we could also rotate it another 1/3 of the way around for a 240 degree rotation, and that would cause this to look the same. And then the next rotation we could do that would cause this to map onto itself would be a 360 degree rotation, which of course doesn't really matter, so we don't need to write that down. But 120 degree and 240, we want to see whether the figures have point symmetry. That would mean the figures have 180 degree symmetry, so this one does not. The next shape on our list is a parallelogram. So if we have a parallelogram and we're trying to figure out its symmetry, we can say, all right, if I'm rotating around the center, how far do I have to rotate this shape before it maps onto itself? How far do I have to go around before I find another side of the shape that matches up to this one? And in that case, that would be 180 degrees around the shape. And since it has 180 degrees, it has point symmetry. The next one, we've got this star shape. It's got 4 points. That's one way to think about rotational symmetry. If it has four parts that look the same, 4 points that look the same, then we can say, oh, if I rotate this a quarter turn, 90 degrees, it'll look the same as it is now. Or a half turn, 180 degrees. Or a 3/4 turn, 270 degrees. It'll always look the same as it is now. And then, of course, since it has 180 degree symmetry, it has point symmetry. And then finally, this oval. How far do I have to spin this oval around its center to make it look the same? That would be 180 degrees, and that means that it has point symmetry. Down here, just some other examples. What types of symmetry does the figure have? Well, this flower is a photo. One thing that I want you to understand is sometimes these photos are a little bit off. So like the veins in this flower might not be exactly symmetrical in the way that you think that they should be. We're using the overall shape as our idea. So in this case, we're looking at lines of reflection that go through the flower shape. So there's 1 through that petal, 2, 3, 4, and 5. So this shape has 5 lines of rotation. And it also has, 5 lines of reflection. What am I saying? 5 lines of reflection. And it also has rotational symmetry because it has 5 points that look the same. So if we rotated around 1/5 of a circle, or 72 degrees, it would look the same as it does now. And if we kept rotating around 72 degree increments, so 144 degrees, or 216 degrees, or let's see, 280, what's 216 plus 72? Let me check. I am not good at doing this math in my head. 216 plus 72, 288. And then, of course, 360 degrees would be after that, but 360 is a full rotation, so it doesn't count as symmetry. So that would be rotational. This other picture looks, I think, like a Candyland card almost, but it has a dot in each of these corners. So that keeps it from having any lines of symmetry. This line is not going to make the shape match up directly onto itself, and neither is this line because of those dots in the corners. We also know that a rectangle doesn't have diagonal symmetry like this because the corners of the actual rectangle would not match up along with each other. So it doesn't have any symmetry reflections, but if we think about putting a dot in the center and rotating it around the dot, it does have 180 degree rotational, which also counts as point symmetry, and that's the only kind that that card has. And then finally, we can use symmetry to do various things. So a company CEO wants a new logo that looks the same for each rotation of 120 degrees and has at least 2 lines of reflectional symmetry. What is a possible logo design? So when I'm thinking of this, I'm thinking, okay, if it has 120 degree rotational symmetry, that means that 1/3 of a turn is going to make it look the same as it did before, which means that I could use a triangle, an equilateral triangle, because I know an equilateral triangle would have that same property where 1/3 of a turn would make it look the same as it did before. And that triangle also has 2 lines, at least by having 3, of reflectional symmetry. But of course, on its own, this is not a logo. So we would need to do some more designing if we wanted to make this into a logo, right? So maybe I could go like this. I don't know. I'm just giving you some ideas here. When we have these questions where we want to make a logo or make a design, we want to make sure that we're actually designing something and not just making this exactly the same as it normally would look here. So for example, this could be a logo that I could use because this would be still this equilateral triangle that when I rotate it around 120 degrees, it's got the same look to it. And I could still draw these lines of reflectional symmetry and it would still work there. So again, there's lots of ideas. I could also make this shape based on a hexagon because a hexagon is going to have 60-degree rotational symmetry, which means that it also has 120-degree rotational symmetry. And I could, do some stuff inside my hexagon and make this the logo or something. So there's lots and lots of ways that you can do these problems. When I look at your paper tomorrow, I want to see a design on your paper that is not one of the designs that I've created here. I want you to do a little bit of thinking on your own here. So anyways, that is all I have for you with symmetry. I told you it was pretty simple. Of course, let me know if